Have you ever been amazed by the sophistication of AI chatbots like Google Assistant and ChatGPT, which enable interactions that are not only incredibly fluid, but also closely mimic the nuances of human dialogue? Along the groundbreaking revolution in protein folding, a leap forward in speeding up drug development. This innovative use highlights the versatility and potential of transformers beyond language processing. With that being said, welcome to the informative video by Shaurya Tiwari on embeddings and transformers in generative AI. This versatility of transformers showcases an exciting era where AI's potential is boundless, from enhancing everyday convenience to accelerating the pace of medical breakthroughs. Join us as Shaurya takes you through the realms of embeddings and transformers in generative AI, unveiling the magic behind these technologies and their impact on our lives. Speaking of language, let's define natural language processing, NLP, in the context of machine learning transformers. These models have revolutionized how machines understand and generate human language, providing a deeper context than ever before. We'll also examine text sentiment analysis, showcasing how transformers can interpret the emotional tone of written text, from positive to negative sentiments and everything in between. Further, we explore the intricacies of part-of-speech tagging and text summarization, essential tools for breaking down and condensing large volumes of text into manageable, insightful summaries. Our journey continues with a look at generative models for NLP, where transformers not only understand but also create new, original content based on learned patterns. Finally, we're on the brink of discussing the tokenizer concept of transformers, a crucial component that bridges human language and machine understanding. But let's save that deep dive for another time. Stay tuned for more insights into the ever-evolving world of AI and machine learning.
Tokenizer. A tokenizer breaks unstructured data and natural language text into chunks of information that can be considered as discrete elements. The two most common versions of tokenizers are the tokenizing by words and the tokenizing by sentences. Tokenizing a text by word allows to identify words that come up particularly often. For example, if you were analyzing a group of job postings, then you might find that the word Python comes up often. That could suggest high demand for Python knowledge, but you would need to look deeper to know more. When you tokenize by sentence, you can analyze how those words relate to one another and see more context. Stemming. Stemming is a text processing task in which reduces words to their root, which is the core part of a word. For example, the words helping and helper share the root help. Stemming allows to zero in on the basic meaning of a word, rather than all the details of how it is being used. Stemming a word or sentence may result in words that are not actual words. Stems are created by removing the suffixes or prefixes used with a word. Now let's look at word embeddings. Word embedding is a projection of a word, consisting of characters into meaningful vectors of real numbers. Let's start by looking at a 3D plot that explores the relationship between men and women. Watch how they're connected in the space, almost like a dance, reflecting the interactions between groups, showing how men and women are closely linked. Now, let's dive into another plot that explores how words relate to each other through verb tenses and stemming. See how words like walking and walk share a space, revealing the fascinating connections between language forms. Our final plot takes us on a journey around the world, exploring the relationship between countries and their capitals. Notice how Italy and Rome, China and Beijing are related with each other. Each point on the plot is a pair of a country and its capital, forming a visual map that echoes the connections we find on the globe. Now let's talk about one-hot encoding. One-hot encoding is a simple method for representing words in natural language processing, NLP. In this encoding scheme, each word in the vocabulary is represented as a unique vector, where the dimensionality of the vector is equal to the size of the vocabulary. The above shows an example of how one-hot encoding works for the matrix. Now that we know what are word embeddings, let's structure them into a layer. Embedding layer A. Standard approach is to feed the one-hot encoded tokens, mostly words or sentence, into an embedding layer. The position of a word within the vector space is learned from text and is based on the words that surround the word when it is used. The above is one-hot vector for encoding the keyword cat. We take dot product of one-hot vector with the embedded weight matrix, which gives us the new embedded vector. Position encoding. Positional encoding is used to provide a relative position for each token or word in a sequence. When reading a sentence, each word is dependent on the words around it. An example is the word trunk. In one instance, it could be used to refer to an elephant using its trunk to drink water. In another, it could refer to a tree's trunk being struck by lightning. Let's take an example of sequence. I am a robot. We first token Z our sequence and input it into our positional encoding matrix. But before that, let's take a quick run through of the trigonometric sine function. This is a quick recap of sine functions. You can work equivalently with cosine functions. The function's range is -1 + 1. The frequency of this waveform is the number of cycles completed in 1 second. The wavelength is the distance over which the waveform repeats itself. The wavelength and frequency for different waveforms are shown thusly. The above shows the formula for calculating the each positional encoding. Let's take an example of the phrase, I am a robot, with n = 100 and d = 4. The following table shows the positional encoding matrix for this phrase. In fact, the positional encoding matrix would be the same for any 4-letter phrase with n = 100 and d = 4. The positional encoding layer sums the positional vector with the word encoding and outputs this matrix for the subsequent layers. The entire process is shown. Till now, we have learned how words are embedded and weighted. Now let's focus on how words are given attention. Imagine you are trying to understand a complex image or translate a sentence from one language to another. Your brain instinctively focuses on specific parts of the image or particular words in the sentence that are most relevant to your task. This selective focus is what we refer to as attention, and it's a fundamental aspect of human cognition. Let's ask a simpler question. How would a human know this? How did you figure out these two settings? The way you and I did it was probably to look at the neighboring words. In the first sentence, the word river was the one that hinted at the nature setting, and in the second sentence, the word money was key to the financial setting. So in short, we need a way to use the other words in the sentence to understand what context of the word bank we want to use. Imagine that the words bank, river, and money are all attached on a corkboard. Furthermore, this corkboard contains all the existing words, and in such a way that two words that are similar are close by. Now in this corkboard, bank, river, and money are not exactly close by. However, what you do is take the word bank and move it slightly towards the word river. Call this word bank 1. Now take another copy of the word bank and move it slightly towards the word money. Call this one bank 2. Now consider the following two modified sentences. Modified sentence 1, the bank 1 of the river. Modified sentence 2, money in the bank 2. Now we will utilize what we learned till now to create some weighted embeddings. For example, let's say that I want to move the word bank 10% closer to the word river. I now think of the word 0.9 bank plus 0.11 river. That is, bank 1 is 90% bank and 10% river. Also, let's say that bank 2 is 80% bank and 20% money. So let's say these are the modified words. As you can see, bank 1 is closer to river and bank 2 is closer to money. As a matter of fact, bank 1 is on the line between bank and river, 10% along the way. Similarly, bank 2 is on the line between bank and money, 20% along the way. Thus, the attention mechanism managed to split the word bank into two words and use each one in the corresponding sentence. So in order to calculate the embeddings of bank 1 and bank 2, we simply do the math component-wise. That means for each of the two components of the vector separately. We get this. Transformers excel at sequence-to-sequence learning, taking a sentence and transforming it, be it for translation or summarization. They handle machine translation, text summarization, question answering, and generating coherent text. Now let's introduce the encoder. It processes the input sequence, capturing meaning and context, the source information. Following that, we have the decoder. It uses the encoded information to generate the output sequence, step by step, considering both the encoder's output and its own past generated words. Now let's draw an analogy with friends planning a trip. Imagine planning a group trip. Each friend has unique preferences, destination, activities, budget, and dates. These preferences mirror the words in a sentence for a transformer, each holding importance. Understanding the significance is crucial. Adventure activities may weigh differently than choosing a destination. Embedding translates preferences into a format for quantitative comparison, akin to assigning values based on importance. Sequencing matters in planning, just like in language. Positional encoding notes the order of preferences, ensuring timing influences the planning process, like how word order affects sentence meaning. Transformer blocks and feed-forward networks. Now explore all possible options for each preference. Transformer blocks, with feed-forward networks, analyze options efficiently. Adjusting weights and biases, these networks focus on promising options. Not all preferences are equal. Attention mechanisms let you focus on the most relevant ones. If choosing a destination, preferences about destinations weigh heavier. It ensures contextual understanding and improved performance. Finally, the softmax step is like making an informed decision about the trip. It involves looking at all discussed options to choose the one that maximizes overall satisfaction. The transformer model breaks down individual preferences, considers their timing and sequence, engages in detailed discussions, and makes informed decisions. It captures the complexity of language, leading to nuanced and contextually appropriate decisions. Thanks for joining us on this swift journey through transformers. Stay curious, keep exploring the world of machine learning. Until next time, cheers.